Hello, welcome back. So from the last class, basically the last video, the live stream that we had, we were trying to understand what PyTorch is, and also we created a small regression model. I'm assuming that you already know what regression model is, as you are starting off with the deep learning. Um, so basically, regression is a supervised form of learning where you have some inputs and you have a label. So, for example, house price prediction would be one of the famous examples out there, which means that you have one variable, let's say the number of square feet, the number of rooms in your house, and the label would be the price. So you have a data set of these, and then you want to estimate what functions will be approximated using, let's say, deep learning, so that I can find out the price of a new house. Okay, something like that. Okay, so last time we did use NumPy to create it, and if you remember, we created a dummy data set, and we created our own function. So basically, this is the function. This is it's a linear function, right? Equation for a line, basically, and x is the input and y is the output, and b and w's are the parameters, the learnable parameters, the actual things that are updated, actual numbers that are updated when you are doing the training, right? Okay, so let's get on with it. So last time we did the whole thing. We created x train, x y train, and the data set and the validation set, training set, right? And we computed all the necessary things from the we also had a session on mathematics as well, right? And we estimated the value of b and w using numpy and basic calculations, right? So the final model was fitting something like this. Okay, looks good. As you can see, uh, this one is the intercept, that is b. So b's value is almost 1, which was the actual true value, right? Actual true value was 1, and so is w's value. It was the true value was 2, and we can and our model estimated it's around 2, right? So we're approximating the actual values, and we ran the whole loop for almost 1,000 times, and did the updation was happening here. Okay, so we're gonna follow the same step, but now everything will be uh, in PyTorch, and PyTorch has few tricks up its sleeves, so we're gonna look into that. Okay, cool. Let's start with PyTorch. Just to recap the tensors that we had, the first live class that we had. So uh, tensors were basically a way of representing numbers, right? So there are scalars and vectors and matrix and tensors. So for all that you care about, there's scalar and then tensor, because vectors, matrix, all of them are mostly just generalized and said they are just tensors, right? So all you care about is there are numbers that are just numbers, for example this ones, and there are some form of arrays, right? This is an array, and this is supposed to be an array. As you can see here, this is an array, this is an array, right? So numbers and all this kind of arrays would be called tensors. Okay. Okay, so few basic things that will be used so many times that you literally cannot live without these guys. Basically, what is the size of the array? The dimensions, basically it tells you what dimension the array is. So shape and size. Okay, okay, and then let's say if you have a scalar, it does not have any shape, right? And then view is basically a way to change the dimensions of your tensor. Okay, there's another way, there's a reshape as well, just like in numpy you have reshape to change it. So the basic difference is basically the view method only returns a tensor with the desired shape that shares the underlying data with the original tensor. It does not create a new independent tensor. It's using the actual tensor. So, uh, so that would be the only reason why you would use view. Most of people use view. Okay, so reshape method may or may not create a copy. The reason behind this apparent weird behavior are like beyond the scope of this session, but this behavior is the reason why view is preferred over uh, what do you say, view is preferred over reshape. Okay, so if any changes are made into the original tensor, so this was the original tensor and now we are changing it, one of the values, right? And that change will also be reflected in um, the new tensor that was created using view, right? So that's the reason people prefer view over reshape and PyTorch. But yeah, you have both of them. Okay. Okay. So now if you want to copy something, you want to create a tensor out of another tensor, we can use like new tensor method to really copy it into a new one. Like, so this new tensor can be used to actually copy it into a new, so this one will have a different address now, and if you make any change to that, the original tensor does not change. That's the good point about it. Okay, so new method is there. There's a clone method as well. You can, sorry, new method is there. As you can see, the value was changed to 3, but the original matrix did not change. The value was 2, and but the new matrix, that different matrix, is actually different from uh, the matrix that it was created from. So they basically, in Pythonic terms, I would say or more technically speaking, they share they share different IDs in the memory, right? Okay, so and there's clone as well, and you can basically what it clone is, if you want to copy all data, that is duplicate the data in memory, you have two methods, that is new tensor or clone. Okay, cool. So it seems that Py PyTorch prefer that we use clone together with detach instead of new tensor. Both way accomplish the same result, but the code that you see here is much cleaner, you know. So you might want to go with clone instead of new tensor. I have also seen people using clone over new tensor. Okay, the original tensor matrix is left untouched, as you can see. Okay, cool. um okay, so now let's talk about what is CUDA and maybe just what is GPU and all that, right? So mostly what happens is, all the deep learning must have heard, um, big companies are looking for more and more investment into their GPUs. They want more GPUs, and that's the whole reason why NVIDIA is at the top of the game right now. And you see that all these deep learning architectures, they require a lot of compute, and not just compute in a sense, but parallel compute and parallel processing and stuff. So GPUs are the best way to go about it. There are LPUs as well, new thing coming in the market. So apart from that, so basically you have CPUs and your GPUs, right? And if you want to use, so tensors are built, the PyTorch is built, or tensors are built so that they can work on GPUs. They can leverage that parallel processing and give faster inference and faster training time and all that. Okay, so uh, so your computer or your PC may have a GPU. You might have an NVIDIA's GPU or AMD, whatever. So CUDA is actually developed by NVIDIA. So I guess you can only use it with NVIDIA GPUs. Um, I don't know. I don't quote me on that. They might change something. So basically, uh, you can now change these tensors. So right now, till this point, we had all these tensor loaded in CPUs. That is, if I'm using Colab right now. So Colab has its own GPU also and CPU. For example, I am not using the GPU as of now because I don't think I need that for the demo that we're doing. We're not training anything. So, and it's also recommended that you also not use GPUs whenever, only use it whenever it is required, because they also have to, the collab in the backend, they also have to do some resource allocations and all that stuff. So unless you need GPUs, then only go with GPUs. Okay, so you can change the runtime from here and change it to GPUs. I'm not doing it. I'm just keeping it all in CPUs. Okay, cool. So you have this tensor that was from the xtrain tensor. Okay, so basically that xtrain I want to change into a tensor. It was actually a numpy. It was a numpy array. I will probably show it once. Okay, you see this. If I go and do this, it's a numpy array, right? ND array. But now I want to change it into a PyTorch tensor, right? So this is the method that helps to do that. As tensor. As tensor, you would use it to change it. There are other methods as well. We will come across all of that. Okay, cool. Uh, by the way, I forgot to mention something. This detach part, what it does actually here in this scenario is to actually remove this tensor from the computational graph. I don't know if you remember, I just mentioned computational graph in the last live session. So basically, it's like all the computation that's going to happen. We will discuss about that more in this very live session. So we will talk about what it means to detach from the computational graph. Okay. So don't worry about that as of now. Okay. So where were we? We were at changing those numpy tensors into numpy arrays into PyTorch tensors. Sorry. So what we see here is basically how to do that. You have the xtrain and xtrain tensors being changed using as tensors. Okay, and you can change the, so by default torch always go with float 64, which requires more memory. If you want to save some memory, then okay, I just got a notification. Okay, if you want to save some memory, then it's advisable to use float 32 or even float 16 or int, whatever. Okay, then coming to the next part, that is, mm, so there are other ways. As I said, there are other ways to do the same thing. You can take, as I did before, you can take a dummy array from as a numpy array and do it using as tensor. And so to modify the array right now, you can see the actual the tensor is also being changed. So it's basically pointing to the same array. It does not create a distinct copy of it, different. Okay, cool. And you can also convert the tensor into numpy using just this function. Okay, so now we were talking about GPUs and CPUs, right? So in GPUs, the easiest way to do that, so now you have a tensor that you had a numpy that was in CPU. Now you created a tensor that was also in CPU. Now I want to now send it to and load it in my GPUs. So if that is the case, then you use device is equal to CUDA, which is the name for the GPUs. Uh, okay, if this function is available. So if this is true, then I want the device to be CUDA, or else it can be CPU. For our case right now, it will be CPU. If I run this and I see for myself device, this is CPU. So I'm not using CPU right now. Okay, and you can also check this out. So basically, this function actually tells you how many CPUs. For example, your computer can have multiple CPUs. You can have multiple 8040 CPUs, right? So it lists out all the GPUs that you have. Okay, cool. Hmm. So the way to put these tensors from CPU to GPU is by using this to function, to device. So now the tensor that was with us, the extrain tensor, first we change into a extrain numpy array, we change into a tensor, and then we are sending it into the GPU. Cool. I hope that works. And I hope that makes sense. Okay. Okay. Let's go ahead. There are a few more examples. This is NumPy array. This is what a tensor looks like. Floating tensors, and back to NumPy. I have already shown you this. Or this is the other way too. First change so as this is in the GPU. What you do is you put it into the CPU, and then only you can change it to NumPy. You cannot directly change a tensor that is in GPU into a NumPy, because NumPy does not support that. NumPy cannot, the arrays that you initialize in NumPy, they do not support GPU. Okay, so always remember, if you get an error like that, so probably um, it's because of some, and mostly the error that you will find in PyTorch would be related to um, loading it in CPUs and GPUs. If any variables is not detached, or sorry, not detached exactly, if it's not removed from CPU before using it, or in the NumPy or something, it can be a problem. Okay, so let's get on with creating our model in PyTorch. So let's create the parameters as we did for the true values of B and W. We are going to do the same thing. Now there are a few ways to go about it. Okay, the first way is to initialize B and V just randomly, just like so. We are using torch.random. Random basically is any random number that is sampled from a normal distribution. So you see this one and this one was sampled for the value of B and W, and just like NumPy, we can set the seed here. Okay, now the numbers are different. It's not the same numbers from NumPy, because the seeding methods can be different in different package. Like NumPy has a different way of uh, NumPy will have a different seeding, and PyTorch will have a different seeding. Okay, but if you're using PyTorch, if you are using the same code, and if you're using the same code number, that is 42, then you will get the same random number. So cool. This is one way. So way is basically you're telling him I want one random number from a normal distribution, and let's see what this is in a time, and I want the data type to be float. That's all. Okay, and now let's talk about what is this required grad. Okay, what it essentially mean is basically um, you want your PyTorch to do all the work for you. You want PyTorch to create the computational graph, all the necessary or all the necessary calculations that you need to do, right? Y equals to mx plus c or something, right? You are creating this graph of x is coming in, and it's been multiplied. It's been like multiplied with m, hmm? And then the whole thing is coming and being added with C. You want it to create this kind of a computational graph, and not just that, you also want to tell the compiler or PyTorch that I want these guys as my parameters, in a sense. Okay, in a sense, that's what you're doing. You're telling PyTorch that I want these guys to be my parameters. So can you please make sure that you keep all the gradients when you are going in back propagations. Make sure that the gradients of x and m are stored with you. I want them to be in the computational graph. At the same time, I not these guys. I'm sorry, not m. Um, it's x and c. These two guys. Okay, so these are the uh, variables. So in our equation, it was actually b plus omega x, right? So um, so what we can do about that is mm, these two guys were the parameters. So I want the PyTorch to know that keep them in the computational graph and store their gradients because I'm going to update them in the future. Cool. So that's what required grad does. Now required grad can also be initialized in different ways. So we are going to do that. The second method is to run it. So this one has been initialized in the CPU. As you can see, it's not been sent to the device. So to send it to a device, just do this to the device, right? Cool. And the third method would be to this actually you see the shadow the gradients. It's actually no more in Py, PyTorch 2, but it was there in PyTorch 1. Okay. So the third method is simply first you create both the parameters and then send it. Then do the required grad, right? So that's also one method. Okay. Cool. So we have initialized W and B. Okay. Now finally, we are gonna do the most optimized method to do all that stuff is just put everything inside one. That is one number you want, and the required guide is true, and the data type that you want, and also the device that you have. This probably would be the method that you want to go with. Okay. So let's get to autograd. So that you already know what autograd is. It's basically calculates the gradients for the variables in the computational graph all by itself. Okay, so PyTorch does that for you, right? So you have this is the forward pass. Basically, you have let's say you have this, and the x is coming from here, right? And it's been multiplied with w, and it has a bias, and it comes at y. So this is your neural network. It just has one neuron, as I last time I told you, just one neuron. Okay, so that's all it's happening. So this is the x train tensor, and then w, and of course the b. Okay, so forward pass has been done. Cool. And now we calculate the error just like we did before, and the loss function, it was squared and mean. I told you why it was squared and mean. And then the loss dot backward. As soon as you hit this, the computational graph is created, the gradients are computed. So let's find the gradients. Okay, as soon as you hit loss backward, you have both of them. Okay, now you're checking. So one more thing you need to be sure about. Okay, just so you know, like I have kept these two guys, right? Let me color it in different. These guys have required grad equals to 2. That is, they are in the computational graph. Every calculation that are done on this will also have required grads too. For example, y hat is a function of these two guys, right? You can see they are in the equation, and error is also function of these guys because these guys are um included in this, and which is coming in the equation. Then again, the loss, it depends upon error, which in turn depends upon w and b. So all these guys will also have the required grad equals to 2. Okay, so make sure that happens. So error required grad, that is true. Y hat required grad, that is true. B, that is true. W, that is also true. Only thing that isn't true is the ones that we did not define. For example, Y train and X train, their required grad is not true because we never defined it, right? Only place where we did it was for W and B, and that is what we want. We don't want to, we are not actually changing the training data or labels, right? We are not going to update them in the future. So you don't want that. So you can see their required grad is false. Okay, now let's see what is the gradient that that PyTorch has computed basically in this computational graph. Okay, given the value of uh, given the value of W and B. The initial values were something, right? So initial values. Let me see the initial values once. So the initial value of B is 0.3367 and W is 0.1288. Cool. I'm printing out the gradient values that will be subtracted from the actual these values. Okay. So the gradient value was computed by PyTorch. You didn't have to do actual, for example, in the previous one, Tempai we actually did that, right? You remember? Yeah, computing the gradients. We did not have that. We actually solved the gradient using like mathematics and just put it here manually. Okay. Um, hmm. It's created an autograd comes in and you have the gradients. Okay, you can now you can also see the gradient for all the parameters that you have. For example, if the network had some other parameters that also had required grad equals to true, you can find the grad for that. So they will also have a gradient in the memory. Okay. Okay. So now one thing we want to talk about is basically what happens if I run this again. Like this thing is basically the first three steps, right? And then the update comes in, and you do it in a loop. So if we are doing it in a loop, that means it's gonna happen twice, thrice, and how many times you are the epoch runs, right? If I do it again, let's say again I'm running this, and again I am doing this and this and this. Okay. Okay, I will show you that. Wait. Uh, mm, B is not computed again. Let's do this once more. Mhm. Got the answer. Hmm. Okay, so the gradients have changed. If you noticed, okay, I will show you what exactly it were, and then we can talk about it. So gradients, okay, the actual values were this and this, and the gradients that we found for the first time, that is when it was done for the loop was run for the first time. The gradients were b dot grad is equals to minus 3.1125 something, and w dot grad equals to minus 1.8156. Okay, again I'm running the loop, which is gonna happen in the whole epoch thing, right? Running it again, you see the numbers have changed, right? I didn't do anything. I literally did not do anything, right? The gradients have changed. Again, this one is now minus 3.6313. And if you notice, it's literally the double of this one. Literally the double. Basically, it's adding it again. So what it's called is, it's called something called as gradient accumulation. And you don't want this, like you really don't want this in your code because it's not desirable. You want to make the updates, and when the update is done, you want the gradient to be calculated again. But here in this case, it's calculating the gradient, of course. At the same time, it's also adding them up all together. I hope that makes sense. So what it basically does is, uh, every time if you are going through the loop, it adds up the gradients and accumulate it. If it's 1,000 times, then it adds the gradients up 1,000 times, and because of that, the training will be wrong. Okay, so you don't want that behavior from this. What you need is, you have to change the gradient to be 0 every time the loop runs, and there is a method for that. Okay, so uh, we need to use a gradient corresponding to the current loss to perform the parameter update. We should not use accumulated gradients. So if accumulated gradient is a problem, then why does PyTorch do it in default? That's a good question. And let's see what it basically was used. So this behavior can be useful in circumstances of any kind of a hardware limitations, where you have limitations in your GPUs, right, or CPUs, whatever. So during the training of any large models that you have, so the necessary number of data points in a mini batch may be too large to fit in a memory or in a graphic card like a GPU card, right? So one can solve this by just buying, a bigger graphic card, but that is not the way, right? We have a better method. That is, we can split this mini batch into more smaller batches, and then compute the gradient for those smaller mini batch, and then accumulate them to achieve the same result as if computing the gradient on a full mini batch. Okay, so I know it can sound a little confusing, so don't worry about it. It's little out of the scope of the whole thing, but all you need to know is, when you're running a loop, the first step, the forward pass, then calculating the loss, and then calculating the gradients using back propagation, and then updating. In this process, the gradients that are calculated in the first iteration will be accumulated over time, and you don't want this behavior, and we will mitigate this behavior using a very simple function called as 0. So as soon as you hit this, I do this, okay, the gradients will become 0, and if I run it again, now you can see the gradients have become 0. Okay, you need to do this in every loop. That's why we want to do that here. That is the proper, the whole thing, we are coding it out here. Okay, the updation of the parameters, how it happens. Okay, let's see. So I have divided the whole thing here into 3 parts. So it's basic loop. You have the B and the W's, they are coming in, I mean the parameters of the model, and the number of epochs, how many times you want to run throughout the code. Okay, now if you see properly, the first item that we have is just to update. We have B, right, and we have some learning rates, and we are basically updating the parameters here. And if I run this, okay, I should see. So it threw an error, and it was supposed to throw an error actually, because in this scenario we did not make the gradient 0. Okay, in this scenario we did not make the gradient 0, although okay, I will show you one more thing you have to understand. Okay, uh, it did give out this for the first attempt. I don't know, you can see that the first loop that it ran, it did give out the value of B and W, and that are actually different from the values that was initialized to. These are the values it was initialized, 0.33 and 0.12. It's actually different, but as soon as I hit the next attempt, it fails to, and the error is the grad required for tensor that is not delivered is been accessed. could not be calculated, and this is a pretty long thing. Okay, this is the first attempt and it did not work. Okay, let's see the other method. Okay, so basically, if you want a deeper explanation to this problem, we can have a discussion on that too. So in the first attempt, if we use the same update structure as in our NumPy code, that is what we are doing here, right? If you see the first attempt, this is exactly the code that we did in the NumPy implementation of this simple linear model, right? We will get the weird error below, and that error, but we can get a hint of what's going on by looking at the tensor itself. Once again, we lost the gradients while reassigning the update results in our parameter. Thus, the grad attribute turned out to be none and it raises the error. That's why you see the the non-type object has no attribute 0. So we lost basically when you are doing this reassigning the parameters. Here you see the reassigning of the parameters. What happens is it's not in place method, right? There are two types of updation. There's one that is in place and this is then reassignment, right? So you might think, what if I just reassign it, right? What if we reassign the whole thing instead of doing this? What if you do an in place operation instead of reassigning? Cool. Let's see if I run this, you find a different error this time. A leaf variable that requires grad is being used in an in place operator. So now why does that happen? It that uh, turns out to be the case of too much of a good thing. The culprit in this problem is the dynamic computational graph that was created. So every Python operator that involves any gradient computing tensor or its independence. Okay, what is happening is basically um, the leaf variable that requires grad is being used in an in place operator. So the way the graph is initialized, you cannot do the in place. This is also not working for us. Cool. And let's go with the third. And now this is where uh, basically everything will work out. Let's see. So what we want is this. Now it works and you almost got the perfect answer for B and W, which was supposed to be 1 and 2. And what is happening here? What exactly is happening here? So what happens is, if you are doing this operation of updation, every operation that happens, for example, the subtracting and the multiplication, of B, it will also be added to the computational graph. You don't want that. And if that happens, that is why the second attempt that we had, this one threw an error, because what it did, it actually changed the B and W. It was an in place operation, right? So B and W were actually changed. That's why it affected the computational graph. And as it affected the computational graph, it threw an error. Okay, I hope that makes sense. Cool. So to mitigate this problem, to solve this problem, we have tosh.nograd. So what it's saying is, now whatever operation is going to happen inside this with this code scope of this line, right? That operations, do not add it to the computational graph. I don't want them. I just want to update them. Don't add this. So for example, this is your computational graph and it will add some other branch to it. B and W will have another branch coming in with the LR into, uh, b.grad or something. So that is another thing added. You don't want that. This is not a part of the actual function that you're trying to build. So that is a problem. Okay, I hope that. And if you are having trouble, what leaf variable, for now, just think leaf variable is anything that has that required grad equals to 2. So basically they are the parameters, or they have the required grad true. Okay, cool. Okay, so that is it. We trained our whole model using PyTorch. That is a simple linear model. And there's a way to visualize it. And let's talk about more about what is this dynamic computational graph that the PyTorch actually generates. And we will have a deeper look in how it works. Probably we'll understand this better now. Okay. So we were doing this. I want to show actually a better example than this one. I did try out few things. Okay. Okay. Cool. Let's start with this one. Okay. This one has, okay, no, we have the same model. We have the same model. Everything is same. The all equations. Only thing is we are not out doing any updation and all that. We are calculating loss. That's it. Till that point. Okay. So you have these two graphs coming in. I hope you see that. And let's break this down a little bit and how to understand this. It's pretty simple. So there are two variables. Though you see the blue boxes. These are the two blue boxes. Okay. The one and the one. Okay. Cool. Now these two boxes, basically the blue boxes, denote all the variables that have required grad equals to true. Okay. All the leaf nodes, you can say, in a sense, or the parameters. So this is your B, and this is your W. I hope that makes sense. I can maybe shade this into blue. It's also blue. Okay. Now coming to the next part, that is accumulation gradient. So when you do this, this happens with every single one of them. Accumulate gradient is something that it tells that this will, all the gradients of these guys will be accumulated because we have the required grad equals to true. Okay, that's all it means. And then here W goes to what? If you see in the actual equation for y hat, we are making the graph of y hat. So y hat has W into x train. So there is a multiplication operation coming in. So basically here is a multiplication operation. A multiplication operation coming in. Okay. This multiplication operation is denoted by mul backwards 0. And again, so what happened here is W was multiplied with something. The something is not mentioned, and it's not mentioned because of very interesting reason, that is simply that x train does not have required grad equals to true, so it's not the part of this graph. Okay, only the variables that have required grad equals to true will be the part of this computational graph. Okay, it was multiplied, that all it's care about, and then both of them came in, and what happened is they got added and they produced a final output of shape 8021. That is what the whole thing is. Okay, so let's go deeper into this. So we were doing for y hat in this scenario. Okay, now let's see what happens if, for example, one of these is not true. If it's false, the B is without any grad, that is, it's false, then it will not create that, it will not add into this computational graph. As you can see, it's just one and then accumulation and multiplication and then add, and something happened, that's it. And but it gave an answer because of course this is happening here, but that gradient is not being stored. You cannot find the gradients, right? They don't have a gradient right now because the required grad is equals to false. Cool. Okay, let's go with this one. I don't want this actually. Okay, now we are trying to find So basically, this is both of them are the same code actually. You don't need this much. This much is not needed here. It's for the y hat, and here we are also finding for the loss. So as I told you, everyone that has the variable that uh, so every equation, for example, in the y hat, it was also had required grad equals to true. So is error, and so is loss. Okay, I hope that is clear why it happens, because all of them are dependent on w and b, which are parameters, and they have required grad equals to true. And as soon as you do find this, and you can see now, I'm just gonna show it here right now. So this is your b, okay, this one is your b, and this one is your w. And of course, they are accumulated gradients. Then if you break down the actual equation, it looks something like this, right? If you break down the actual equation, loss is equals to error. Error is nothing but y hat. Y hat minus y train, and it's been squared and then meaned. Okay, so dot mean will be something like number of mean something. So y hat is what? Y hat is b plus w into x train, right? And the whole thing is subtracted by y train and then squared and divided by n. This is what it is. Okay, so you can see the w is coming in, this one w is coming in multiplied, and b is coming in multiplied then added. You can see w is coming in and multiplied, so w came in and got multiplied with x something, as it's not in the computational graph, and then added with b, and the whole thing, this whole thing was then subtracted. That's why this sub backward, right? And then the whole thing was squared. So that's why you have this paw, the paw function, right? And then the whole thing got meaned. That's why you have the mean backward, and it gave out some output. Cool. I wanted to show you how if let's say x and y also add grad equals to true, then the whole thing would look like this. All of them coming in and same thing happening. This probably is b, and this is w, this is x, and this is y. Okay. Okay, so in this scenario, you can actually see y and x are coming in and getting multiplied, and it's then going in and getting added with b, and all the thing. Then this whole part, all these three variables, and then getting subtracted by y. You can see the subtraction here, and then to the power 2, and then the mean. Cool. That's all I'm gonna do for this class. Next class, as you can see, I have the optimizer already loaded. We're gonna do how to use optimizers, what optimizers are probably, and see how that gradient descent thing happening, and they have functions for that too. Okay, so for example, this is stochastic gradient descent and how it works. Okay, it's very simple, and this loop you literally have to remember them. I mean, it's now you do understand how it works, but yeah, you will be using this a lot, and you will be seeing this a lot in all code bases. Okay, thank you for joining in. If you have, thank you for having me.